Welcome to a lesson with Dr. Powell. Let's take a look at an example of diagonalizing a matrix, and we're going to do this by using kernels or null spaces of certain matrices. Okay, so as we go, we're going to find the characteristic polynomial, which is done by having x's down the diagonal minusing this whole matrix. So x minus 1, minus 1, x plus 1, x plus 1, negative 1, and then 0, 0, 0. We find a determinant. We can, by cofactor expansion. So this times what's kitty corner plus the negative of this times what's kitty corner, which actually just has a 0 determinant. So that's nice. So it's just this times that guy. So we end up getting x minus 1 multiplied by x plus 1 quantity squared, and then minus 1. Okay, so we can work that out. X squared plus 2x plus 1 minus 1, which is just 0. So we get as our characteristic polynomial that times x minus 1, which gives us x minus 1 times x plus 2. So notice we get 3 different eigenvalues. Okay, so we get x equals 1, x equals 0, x equals negative 2, and the corresponding factors for them are x minus 1, x, and x plus 2. Now we're going to think of these factors as matrices, all right? If you multiply those matrices together, you'll get the 0 matrix. Now, in other videos, we used ranges of matrices in order to find eigenspaces, especially if you only have 2 different eigenvalues and the minimal polynomial doesn't have any square factors in it. Now here we have 3 different factors. So we're going to use kernels. We're going to we're going to look at this matrix, which is just this one, minusing 1 down the diagonals, because x represents this matrix. Subtract 1 down the diagonals, we get the diagonal, we get 0, and let's see, minus 2 and minus 2, and then we have 0, 0, 1, 1, 1, 0. Okay. So what we're going to do with this is we're going to find the kernel of this matrix, put it in reduced row echelon form. So pretty much just rearranging a couple rows. If you can think about, we're going to have 2 pivots, this one and this one. This one going up, we can airdrop with a times multiplying by 2 and airdropping up. So it looks like, and then with rearranging, looks like we can get 1, 0, 0, 1. So this guy going to the top row, and we're going to have 2 times negative 2, that's negative 4, plus that 1 is going to be negative 3. And then that negative 2 is going to remain there. So no pivots in this column, 0, 0, 0. So reduced row echelon form. Now from here, from the reduced row echelon form, we can find a basis for the kernel, which will be one-dimensional. We're going to get it from this non-pivot column. It's going to turn into it. First of all, we look at this pivot, which is the first column, and it hits, if we draw an arrow this way, it's going to hit this entry. And since this was in the first column, it's going to keep this in the first row, but change its sign. So we're going to have a 3. Now, similar thing here, since this is in the second column, it's going to keep this in the second row, but change its sign to a 2. And then you think about adding 1s down the diagonal, a 1 would be added there. So 3, 2, 1 ends up being the basis for the kernel. And that's an eigenvector for this particular eigenvalue, x equals 1. So we actually found this eigenspace directly from this matrix. Instead of by looking at the range of these guys multiplied over here, we simply just took the kernel over here. And you can do that individually. So for this guy right here, let's find the kernel. of this matrix. So think of its reduced row echelon form, um, and how that's going to work. So here you think, okay, this one can clear out what's below it, and so it's going to look like a reduced row echelon form is going to be like a one. So I'll just write this reduced row echelon form. We'll just go right to it. 1, 0, 0, and then we're going to have so that's going to be a 0, and here you can multiply what remains by -1. So you get a 1, -1, and that can actually be used to clear off what's below it. So you get 0, 0, 0. That's the reduced row echelon form. Use the same trick right here, and we'll end up seeing that a basis vector will be 0, 1, 1. Okay, and that's the eigenvector for that eigenvalue. Now for this guy right here, we're going to add 2 down the diagonal right there. So we're going to get 3, 1, 1, and we have a 1, 1, 1, 0, 0, 0. Okay, and let's get the reduced full echelon form for this guy. Divide this top row by 3, that would become a 1, and then you can clear off what's below it. It looks like, without too much work, looks like we're going to end up with 0, 1, 1, 0, 0, 0. Okay, and that's the reduced full echelon form. And using the same idea, it looks like we're going to get 0, -1, 1 as our basis vector for that kernel for that eigenspace. Okay, so using that, we can come up with our matrix to we can use this to come up with a matrix to diagonalize this one. Particular, we'll just do it right here since we have them all the information right here. Okay, so so we're going to take this matrix and multiply it on either side by, let's see, we're going to have P and P inverse here, and that's going to equal a diagonal matrix. This diagonal matrix is simply going to be a matrix with the eigenvalues going down. So 1, 0, -2. And then in the corresponding positions for the matrix P, we put the respective eigenvectors. So here we'd put 3, 2, 1 corresponding to the 1. We'd put 0, 1, 1 corresponding to the 0. And we'd put 0, -1, 1 corresponding to the -2. And with that, then if we find the inverse of that, we can multiply this out, get the diagonal, and we have successfully diagonalized this matrix right here. Thanks for watching.